Okay, I welcome you all for this special lecture, Mangala Naralikar Memorial Lecture. As all of you know, Professor Mangala Naralikar passed away a few months back. She was governing body member of Bhaskaracharya Pratishthan, very closely associated to the activities of Bhaskaracharya Pratishthan for many years. She was interested in analysis, especially analytic number theory. She did her PhD from TIFR Mumbai and then taught at various places including Savitribai Phule Pune University, Bhaskaracharya Pratishthan. She was mainly interested in teaching mathematics to school students and writing for school students, especially very small kids, primary schools and all that, and she contributed immensely in that area. In particular, Bal Bharati textbooks, last 10-15 years, she did a very remarkable job, excellent textbooks. I had opportunity to work with her in one of those committees, and she was very innovative in writing textbooks for small kids, which is a very non-trivial and tough job, by the way. And she was very innovative. She used to write poems, she could think of pictures, and even complicated concepts for small kids she would look it very simple. So after her sad death, her relatives proposed this scheme of having this lecture series at Bhaskaracharya Pratishthan, and we are happy that today Amartya Kumar Dutta is present here and he will deliver this special memorial lecture. Most of you know him very well. He is a well-known scholar in algebra. He did his PhD in TIFR Mumbai. Yeah, under the guidance of Professor Bhatodekar, who is also here and associated with Bhaskaracharya Pratishthan. He is also known as a very renowned scholar in ancient Indian mathematics, and he has written several articles on ancient Indian mathematics, on works of various people including Brahmagupta, Aryabhatta, and various methods coming from ancient Indian mathematics, and he delivers lectures across the country on this subject. Incidentally, he is here also for this NCERT textbook writing. He is also actively involved. So now NCERT textbook will have this content of mathematics of Indian origin, and he is contributing to that. That is a great contribution in some sense. So apart from his very studious, enormous contributions in algebra, he is also contributing in this ancient Indian mathematics. So I welcome Amartya Kumar Datta again in Pratishthan. He has been visiting, he has already visited in past, and request him to deliver his lecture on emergence of algebra in ancient India. Okay.
So I am really deeply indebted to the organizers for this today's talk at Bhaskaracharya Pratishthan. It is about the genesis of algebra in India, and it is significant for me because Bhaskaracharya, as far as I know, Bhaskaracharya Pratishthan is the first major national institute in India which is named after an ancient Indian mathematician. And we should be grateful to Abhyankar for that. And in fact, I posed this question to our IKS group in NCERT that whether there is any older institute. So somebody mentioned about Aryabhatta Institute in Astronomy, which was founded in 1954. But the point is, in 1954, it was not named after Aryabhatta. The Aryabhatta name came in 2004. So I don't think there is any institute. There are, hostels in TIFR, for example, named after Brahmagupta, Bhaskaracharya, etc., Panini, Patanjali. But a proper institute, I don't think there is any institute. If somebody comes up with a name, please tell me. So therefore, it is, I think, appropriate that I start with a quote from Bhaskaracharya's. So Bhaskaracharya has a book named Bij Ganita, and again here Pratishthan has a role that Sriram Abhyankar's father had edited the Bhaskaracharya's Bij Ganita, and that has been brought out by the Bhaskaracharya Pratishthan. So there is towards the end he justifies or he just says that why algebra should be studied. So, he brings out all the features of algebra, that it is charming for mathematicians as well as applied mathematicians, the astronomers, easily accessible to youngsters. So, these are quotes which can be put in the textbook. Charming for mathematicians and astronomers, easily accessible to youngsters, algebra, the essence of mathematics, which this is now universally accepted, what Bhaskaracharya told in 12th century, is demonstrated here with examples. It is replete with excellence and devoid of defects. Algebra is something, it has to be perfect. So, here again I will tell you, I mean, about this replete with excellence and devoid of defects, what it really means. I think you can understand from another anecdote. So, Abhyankar had proved something called epimorphism theorem, purely algebraically. So, once we were in Bombay IIT and his student, who is also a well-known mathematician, Professor Sudhir Ghorpade, he was informing Abhyankar that there is a topological proof of the epimorphism theorem. I think Abhyankar gave a glare, I did not see that. So, I think Ghorpade withdrew and said, I mean an alleged proof, lest Abhyankar gets offended that some topological proof is mentioned. So, Abhyankar very magnanimously said, what is there to, why say allege? A topological proof may well be 99% correct. And since I was there and Abhyankar was not sure, at that time I was just a student, so Abhyankar was not sure whether I know about the Abhyankarism. So, he clarified to me, very humble to, you see, with a tone of helplessness, you see, as long as you do not algebraize it, I cannot give it 100%. So, you see so the point is that through this anecdote you can understand this, that it is replete with excellence and devoid of defects. Algebra does not leave room for gaps, and this is something he is mentioning in 12th century. Learn it, learn it. Why one should learn algebra? So, padha, mati buddhai. So, for intelligence, acquisition of wisdom, and also it would give you confidence. So, these are features which have been mentioned by Bhaskaracharya. Now, we come to the founder of Bhaskaracharya Pratishthan, Abhyankar, in an article. This was a serious article on survey article on resolution of singularities, but since he himself was involved, so it was partly autobiographical also. So, he says, my journey from India to the United States for doing graduate work. So, Abhyankar did his PhD in Harvard University under Zariski, Oscar Zariski, in the early 50s. So, those days people used to travel by ship. My journey from India to the United States for doing graduate work paralleled the march of algebraic discoveries from India through Arabia to Europe in ancient times. Embarking from the Bombay pier, my boat took the same path by which algebra had travelled from India to Europe via Arabia, where it acquired its current Arabic derived name as opposed to its original Sanskrit name Bij Ganit, and where it is published, not in any newspaper, it is published in Bulletin American Math Society. Now, Abhyankar is not the first to talk about this transmission of algebra from India through Arabia. You can see various people, I mean historians of maths, general scholars, as early as 1895, Swami Vivekananda is mentioning about algebra. Even more it has done in antiquity. See, there is remarkable work done in medicine, but even more it has done in mathematics, for algebra and other things were invented in India. Look at Kajeri, historian of mathematics. Both the form and spirit of the arithmetic and algebra of modern times are essentially Indian. Again, another person dancing, is it not equally strange that algebra, that cornerstone of modern mathematics, also originated in India? So, various scholars have been mentioning about algebra originating in India, and yet we seem to be somewhat apologetic, and there is some kind of that this kind of statement is nowadays considered as jingoistic and etc. So, why this confusion? So, one confusion is of course due to the word algebra coming from the Arabic or rather Persian mathematician Al-Khwarizmi, who wrote in Arabic. And so that is one extreme, that algebra, the origin of algebra is attributed to Arabs. At the other extreme, origin of algebra is attributed to Babylonians, that they did algebra much before Indians. And then it is also attributed to Diophantus. So the confusion is what we mean by algebra. So let us be clear about that in what sense algebra was invented in India. So I will go by my classification. So let us classify algebra, because there is so much confusion, into three parts. So one thing I would say is proto-algebra. So proto-algebra means that algebraic substance, the spirit of algebra is there, but not the external form of algebra. That means x, y, z, formation of equations, that is missing. But otherwise, you see algebraic mind at work. This is what you see in Babylonia. And if you insist on proto-algebra being called algebra, then you see very good proto-algebra in Sulva Sutras of Bauddha. So sometimes when you say algebra was there in Vedic time, that is both right and wrong. If you include proto-algebra, then of course it is there in Vedic. The geometric expressions of algebra formula is there. Second thing, our arithmetic, the decimal system, the methods of doing addition, subtraction, multiplication, division, these are all algebraic, these all involve algebraic ideas. So that is proto-algebra. The next thing is classical algebra, which Abhyankar would call high school algebra. Use of symbols, formation of equations, number systems, what we have been discussing today, that operations with negative numbers and 0 along with positive numbers, identities, formulae, solutions of equations. Then also what is now, algebra is the essence of mathematics, that is the algebraization of mathematics. And also the awareness, the consciousness that there is a subject, there is a distinct discipline in mathematics or scholarship, which we now call algebra, that algebra consciousness. So these are things which are features of classical algebra. The other part of algebra is the algebra that is now taught from college onwards, typically, what is roughly called abstract algebra or modern algebra. Those who are, have gone to college mathematics, you would know about groups, rings, fields kind of things. So that is modern abstract algebra. Now just as classical algebra comes a little late, but before that you have elements of classical algebra in earlier times, like in Vedic time or in Babylonian time. Similarly, you see an anticipation of modern algebra, abstract algebra, in the formulation and study of composition laws in India. Now here comes, if one person has to be identified, that is Brahmagupta. He laid firm foundation. Brahmagupta laid firm foundation of all aspects of classical algebra. So bit of something here, something there may be coming earlier in Diophantus, in Aryabhata, but all these things together first time occurs in Brahmagupta. And what is remarkable is that somebody who laid the foundation of the algebra which is done in school leaped into modern abstract algebra by his formulation and study of composition laws. So all these things occur in a chapter. So Brahmagupta has a chapter called Ganitadhyaya, that is chapter 12 of his treatise Brahmasputa Siddhanta, which is arithmetic and geometry. Algebra is singled out and a separate chapter is written on that, that is chapter 18, which is called Kutakadhyaya. David Mumford, he is a Fields medalist, he made a statement which completely brings out succinctly what I have been saying, that Brahmagupta is the key person in the creation of algebra as we know it, because Mumford is also aware of attributing algebra to Babylonians. So Mumford uses an expression which we can easily understand. Brahmagupta is the key person in the creation of algebra as we know it. So what Babylonians did or what Vedic savants did, that is not algebra as we know it today. So my talk today would be an elaboration of Mumford's statement. So let us see, let me first make a list of the foundational features in Brahmagupta's chapter 18, Kutakadhyay. He gives symbols for different unknowns for the first time. Diophantus gave a single symbol for all the unknowns, and you can see what kind of confusion it will create if the first variable, second variable, third variable, everything is denoted by, let us say, x. So that is not algebra as we know it today. So for different unknowns we have different symbols. So this is Brahmagupta. Formation of equations, algebra of polynomials, how to add two polynomials, how to subtract two polynomials, how to multiply two polynomials. 0 as an integer, which is distinct from 0 as a place marker. The 0 as place marker is much older. It is there in India, it is there in late Babylonia, it is there in Mayan civilization. But 0 as integer, that occurs for the first time in India. And the rules for operations with 0 and negative numbers. Explicit general formula for roots of quadratic equations. Gaussian method of elimination for solving linear equations. And then the big leap, binary composition on abstractly defined unknown set. During my last visit, I talked about this, just on this red colored thing in Bhandarkar Oriental Research Institutes. And announcement of algebra as a distinct important discipline. Nobody had done it before. I mean, at least there is no such evidence. So before coming to this part, the classical algebra, let me just give some sample of proto-algebra in India. So that we go to Sulva Sutras. Now look at constructions like this, that draw a square which is n times a square of side A, which basically means that you have to construct root n times A and not approximately, exact construction. So you can see that what is done. So once you have a length A, you can have as many multiples of it using compass. So you have the base, which is n minus times A, bisect it, and then you also have n plus 1 A and bisect it, and then form an isosceles triangle on which the equal sides are n plus A by 2. So this is n plus A by 2, this is n minus A by 2, and then they say that this vertical is the required thing. This is the construction which is given in Katyayana Sulva Sutra, which clearly shows that they are aware of the algebraic identity in some form, that n plus 1 A whole square minus n minus A whole square is n, or not n, 4n. Or even more remarkable is construct, this is Bodhana's construction of a square equal in area to a rectangle. So this is the rectangle A, this is a bigger side and this is a smaller side. So this is the rectangle, so you have to draw a square equal in area. So what Bodhan says is that complete the smaller square. Then look at its difference. So this part is A minus B, so bisect it. Then what is this? A minus B by 2, but what is the entire thing? That is A plus B by 2, B plus A minus B by 2 is A plus B by 2. Now you draw your arc and meet it in this extended line. So this part is A plus B by 2, this is A minus B by 2, and they then say that this is the side you take. So what are they using? A plus B by 2 whole square minus A minus B by 2 whole square is AB, because this is something which cannot be empirical. So here you see algebra in geometric form. So these are the features of the two examples: exact construction of root n or root AB, no measurement is involved, no approximation is involved, and it uses the Bodhana version of Pythagoras theorem. And Seidenberg, who is an important algebraist and algebraic geometer, in fact, when somebody studies my subject, commutative algebra, one of the earliest theorems he studies is Cohen-Seidenberg going up, going down theorems. And he was also an historian of mathematics. So he talks about this construction of square equal in area to a rectangle. This is entirely in the spirit of the elements of Euclid. Indeed, I would say it's more in the spirit of the elements than the elements itself. So, to conclude, this is, you have geometric expressions of algebra formulae, and you also see that in Katyan's construction, the n was arbitrary. He is not taking a numerical example like 5 or 7. That is also an algebraic thinking. But though there is awareness of algebraic formulae and quadratic equations, I have not given examples of quadratic equations, that also occurs in the Sulva Sutras. So, though there is an awareness of algebraic formulae in geometric form, identities and equations are yet to be formulated explicitly as algebraic expression, even verbally. So, the science of algebra, formal algebra, is at best, you can say, dormant. Now, when I am making this statement, this is not an undermining of the Sulva authors. In fact, this is the greatness of the Sulva mathematicians, the Vedic mathematicians, that they invented mathematics algebraic in spirit and substance much before the genesis of formal algebra. So, algebra, once algebra, formal algebra of Brahmagupta is introduced, mathematics becomes much easier. But before algebra was invented, formal algebra was invented, to do algebraic mathematics, that needed, that needed an enormous caliber. So, one modern example which I can talk about is Gauss, who is regarded as a very formidable mathematician. And that is because Gauss had given group theoretic results before group theory was invented. That is why he is regarded so highly. The same same appreciation you have to have for the Vedic mathematicians. So, this makes the Vedic savants. So, this is not a discredit that they have the symbols. In the absence of symbols, assuming that they didn't have symbols, because there is no evidence for that, assuming that they didn't know algebraic symbols and equations to make such kind of constructions, show them as much greater as algebraists. Okay, now we come to the next part of proto-algebra, the decimal system. So, again here algebra. So, Bhaskaracharya says that algebra is the essence of mathematics. Now, what is the essence of algebra? So, according to Abhyankar, he has a poem, it starts with polynomials and power series, may they forever rule the world. In fact, once in Calcutta during his visit, he was saying that Newton, with his polynomials and power series, is the founder of everything in modern mathematics. So, this is a high place in modern algebra and algebraic geometry that polynomials and power series has. So, this much you remember. Now, you see, to appreciate the decimal system, that how much of algebra there is involved in it. Now, let us say what is a polynomial? A polynomial of degree n is represented like this, and you need not write the coefficient if it is 0. And there is another way of representing polynomials, that is, you just keep on collecting the coefficients, but here you have to put 0 if something is missing. So, let us look at example. Look at the polynomial 2x cube plus x square plus 7. So, I do not have to say what this means, I mean, you know the polynomial, but you have to, if you represent it as a n-pull, then you have to write it as 2, 1 and then a 0 for the fact that x, there is no coefficient of x, 2107. What is decimal system? A number is represented in two ways. One is the Vedic number vocabulary 2107. So, 1000 plays the role of x cube, 100 plays the role of x square, and there is this unit. Or you write it in this form, that is 2107. So, you see that how algebraic decimal system is, thinking in terms of polynomials. So, decimal place value system is nothing but 10-adic polynomial expansion. Now, of course, you can say that being proud of Indian mathematicians, I am trying to see polynomials in decimal system. That is not the case. So, what did Abhyankar say? Newton with his polynomials and power series is the founder of everything in modern mathematics. So, point is that who is associated in the development of mathematics Western development mathematics with polynomial power series, that's Newton. Okay? What did Newton himself say? Look at this, that polynomial and power series, these are conscious generalization of the decimal system. So, Newton said, since the operations of computing in numbers and with variables are closely similar, I was amazed that it has occurred to no one. And by the way, just before Newton, the Indian decimal system had got standardized in Europe in 17th century. And Newton, it says that I was amazed that it has occurred to no one to fit the doctrine established for decimal numbers in similar fashion to variables. So, Newton says that how is it people did not develop this algebra of polynomials after decimal system has come? Especially since the way is then open to more striking consequences. For since the doctrine in species means the mathematics with x, y, z, species refers to that x, y, z. Since this doctrine in species has the same relation to algebra that the doctrine in decimal numbers has to common arithmetic, its operations of addition, subtraction, multiplication, division and root extraction may be easily learned from the latters. Why are you not copying? He is asking mathematicians that why are you not copying things from the decimal system to the algebra of polynomials? This is the genesis of polynomials and power series. And as late as 20th century, so I was talking about this epimorphism theorem of Abhenker. So, he has apart from his initial paper, he wrote a very long what he calls Kyoto paper on elaborating the theorem and its techniques. So, there he says, this is Abhenker, the concept of a strict system of generators of a semigroup. So, this is something technical thing that he is introducing, but the point is that what he is doing, what he called the g-adic expansion, this is a generalization of the idea of decimal expansion. So, this decimal expansion had inspired a very important innovation even in 20th century, an innovation by Abhenker himself. So, one thing I should point it out, that arithmetic is learnt very early, let us say something like multiplication, school children, but the thing is you have to remember the school children did not invent the multiplication rule, they are taught something which is already there. So, learning is easy, that is why it is taught early, but the invention needed algebraic insight, because the multiplication algorithm, whoever invented that, he had the realized and skillful application of the distributive properties of integers, a into b plus c is a b plus a c, and the polynomial like aspect of integers expressed in decimal system. So, let us say 19 into 12. So, it involves the expansion of polynomial expansion of 19, polynomial expansion of 12, and then when you are doing this 19 into 12 in 2 steps, what you are doing? This is 19 into 2 and this is 19 into 10, and then these are added together. So, this requires a high maturity in algebraic thinking. Maybe algebra was not formally invented when these rules were invented, but those who invented the rules, they were very strong algebraists. So, there were algebraists before algebra was born. Okay. Now, we come to Mumford's algebra as we know it. Now, of course, nothing jumps just like that. So, there are things which are pushing you towards the invention of algebra. So, now I come to the next theme, that before Brahmagupta, what were the developments which set the stage for Brahmagupta's invention of algebra? The Sanskrit alphabet itself, its quality, phonetic principle, one sound, one symbol. Algebra is about symbol. The scientific use of symbol that is ingrained in the Sanskrit alphabet, that once it's like let us say ka sound, it can be C and it can be K, and the symbol C can be ka, it can be cha. So, all kinds of things are there, but Sanskrit one, there is no other way of representing the sound ka except by that, and that sound just and that letter means only ka. Then Panini's grammar has symbols and symbolic operations. Pingala uses symbols. We don't know what the symbols are, but he uses symbols for the Laghu and Guru things, and he uses also labels. When he is computing 2 to the power n, he is talking about labels, that is 0 and 2. Decimal notation has also the feature of the Sanskrit alphabet, 1 digit, 1 symbol. So, decimal system people talk about place value and 0 as the two important features, but people do not highlight this thing, that 1 digit, 1 symbol principle. So, what I mean is, let us say 3 in Roman, there are 3 symbols needed for this, or 4, 2 symbols are used. But here for all the 10 digits, there is only one symbol for 1 digit. Now, the Bakshali manuscript I will show in the next slides, these are symbols for the arithmetic operations. So, algebra is about symbols for unknowns, but here you have symbols for arithmetic operations. Aryabhata used vowels as place values and consonants as digits to represent numbers in base 100. So, this I will show in a separate slide. So, this is about, so there are two things. One is the use of symbols, not for denoting unknowns, but in other context. And the other is that there are terms for unknown coming up. In a Jaina treatise, there is a term yavat tavat for the unknown. Aryabhata uses the term gulika. Brahmagupta uses a very suggestive term avyakta and ishta for unknowns. Now, so this is, I will just quickly go through, because this comes before Brahmagupta. Aryabhata's alphabetical representation of numbers, which basically how it has pushed the Indian mind towards algebra. So, these have to be acknowledged. So, Brahmagupta, Aryabhata has the scheme of, okay, so the context is that Aryabhata was writing for astronomy, and in astronomy, Indian astronomy involves gigantic numbers, 4320000. So, they did not use the what you call the decimal representation of numbers, I mean for fractions. So, they expressed everything in terms of integers. So, therefore, the expressions should be very long. So, Aryabhata invented a way of coding large numbers with very few letters. So, his coding is like this. So, you do not distinguish between short vowel and long vowel, because when you are talking, if I say key, then you would not realize that whether I have used long E or short E. So, long and short, no distinction. So, A or A, that has value 1, E has 10 square, so it jumps by 10 square, U has 10 4, Re is 10 6, like that. And the 1 to 25 you denote by Ka to Ma, you denote 1, 2, 3, etc. Ka is 1, Kha is 2, Pa is 21, Fa is 22, etc. And the other unclassified consonants you denote Ya by 30, Ra by 40, La by 50, 60, then the 3 Shas 70, 80, 90, and Ha is 100. So, example, Ma is 25, right. Now, if I say Mu, U is 10 to the power 4. So, Mu is 25 into 10 to the power. So, this even in the decimal system to utter it, it will take a long time. But he says Mu, it means 2,50,000. Now, this number which occurs in astronomy, there is a typo. Actually, I did not prepare the slide, and the gentleman who prepared the slide, he made a typo here. So, it is 432 followed by 4 zeros, not 3 zeros. So, Q grew, Kh is 2, Ya is 3. So, Kh is 32 and U is 10 to the power 4. So, Q is 32 into 10 to the power 4. Similarly, Gha is 4, Ru is this, Ri is this. So, here typo occurs, that is 10 to the power 6. So, this is 4 into 10 to the power 6. So, this is 4 into 6 zeros and then 32 into 4 zeros. So, the whole thing comes as 432 followed by 4 zeros. So, this huge number is represented as Q grid. So, point I am trying to say is this alphabetical coding of large numbers, this is pushing the Indian mind towards algebra. and Bakshali manuscript, which is probably dated 300 AD. Addition, the Sanskrit word is yuta, so the first letter is U. So, U is the symbol for addition. Similarly, let us say division, that is bhaga, that is a Sanskrit word. So, the first letter bha is used for division, and so on. Now, the definition of algebra, that Mumford says it informally, that algebra as we know it, if you try to formalize it, that has been given by Dutta in saying the use of symbols, letters of the alphabet to denote unknowns, and equations are the foundations of the science of algebra. So, with this is the definition which scholars had in mind when they attributed the invention of algebra to Indians. So, now, and as you know, that this is a great step for rapid progress of mathematics. Brahmagupta prescribes use of varna. Varna has two meanings, color as well as letters of the alphabet, and both are involved here. So, varna, the colors are used for the different unknowns, and the symbol is use the first letter of the colors. So, this is explained by his commentator. So, he just gives the principle, the commentator elaborates. The first variable, I told you that there was already a term for that, yavat, tavat. So, that is not a color, but that was already in existence. So, the first, that is x in Indian algebra, is ya, abbreviation of yavat, tavat. Then the list of colors comes up, like kalaka, first letter is ka. So, ka is the symbol for the second unknown. Nilaka, the first letter is ni. Ni is the symbol for the third unknown, etc. Then equations. So, let us give an example of how equations were Indians taught to represent equations. So, equations in India was not left hand side equal to right hand side, but top bottom. So, arrangement was different. So, 10x minus 8 equal to x square plus 1. How it is represented? So, if everything is within quadratic, so here there is no x square. So, this is ya, ya is the first letter, so x, and va is varga, varga means square. So, the first letter of varga is used as a symbol for square. So, ax square, coefficient is 0, x, that is ya, 10, and this is the visible part. Visible part, the word was rupa, and abbreviation is ru. So, ru is 8 with a dot above, dot is to denote that it is negative. Now, right hand side, there is no need for symbol for equality, there was no symbol for equality because it is top bottom. So, x square, here yawa is 1, there is no ya, ya is 0 and ru is 1. This is how equations were represented. And I feel that when equations are taught, that is not the only way to represent equations. There could have been other ways, like in India equations were represented this can be mentioned. Similarly, linear equations, several unknowns. Let us say 197x minus 1644y minus z is 6302. So, how Brahmagupta's commentator explains this? So, x ya, y ka, 1644 with a dot because there is negative, ni 1 with a dot, and what is the constant on the left hand side? Nothing. So, ru is 0, and on the right hand side all these ya, ka, ni, they do not exist. So, ya is 0, ka is 0, ni is 0 and ru is 6302. So, this equation is represented in this way in Indian mathematics. Okay, let me skip this. Next is algebra of polynomials, very clearly defined by Brahmagupta. So, for the unknowns, and polynomials not in just one variable, polynomials in several variables. Their squares, cubes, fourth powers, fifth powers, sixth powers, etc. Addition and subtraction are performed of the like. Like means that 5 square plus 7 square, you just add. So, x square is like. So, 5 x square plus 7 x square will be 12 x square. But 5x square plus 2x, just leave it as that, because x square and x are unlike. So, for the unknowns, there are squares, cubes, fourth powers, fifth powers, addition, subtraction, and performed of the like. Of the unlike, they are stated separately. So, what you do with 5x square and 2x, just state them separately, 5x square plus 2x or 5x square plus y. The product of two like unknowns is a square. So, 5x into 7x, that will be 5 into 7 and x square. The product of three or more like unknowns is a power of the designation. The product of different unknowns is called bhavitaka. So, it gives a name for it. So, x y, x times y, that is a separate symbol. The rest of the operations is as above. So, as clear as it can be, the polynomials of the algebra of polynomials of several unknowns is stated by Brahmagupta. Now, the negative numbers and 0, that is today's topic of discussion. So, I am not giving the full list because I knew that there won't be time for that, but I would like to point out the mathematician Felix Klein, what he had said. Let us realize once and emphatically how extraordinarily difficult in principle is the step which is taken in school when negative numbers are introduced. Here for the first time we meet the transition from concrete to formal mathematics. The complete mastery of this transition requires a high order of ability in abstraction. And there is a separate section in the Kutakadha Brahmagupta, Atha Dhana Rina Shunyanam Sankalang. Now we are dealing with positive, negative and 0. A separate subsection is there. So, negative numbers are used freely and the term is coming from debt and possession, because it was called Rina and Dhana. And this was introduced in Europe only in the 16th century, and there was a resistance from several mathematicians well up to 19th century. So, I have given quotation, I hope it would get introduced by De Morga, that he raises strong objection to negative numbers in mathematics. This defined 0 as a minus a. This is the earliest use of 0 as an integer in algebra, and in Bourbaki's History of Mathematics, this point is emphasized very much, that it is due to the Indians that 0 has been introduced as a number, as distinct from place marker. So, in retrospect, he was like a modern algebraist who envisaged integers as a ring. So, all the laws of science, is a very long list of rules. Minus into plus is minus, minus into minus is plus. These rules are stated, a into 0 is 0. The next is quadratic equations, the general formula for the solution of the quadratic equations. So, strategy is the eliminate the middle term, and it is interesting that the term for quadratic equation was Madhya Harana. Madhya is middle, Harana is elimination, elimination of the middle. This is the term used by Brahmagupta. And the idea of completing the square, obviously Brahmagupta knew about the completing the square, that is why the Madhya Harana, but Brahmagupta does not state the idea. This was stated by Sridharacharya, but that treatise is lost, and Bhaskaracharya has acknowledged Sridharacharya. So, therefore, it is called Sridharacharya's method. Now, so the formula was known to Aryabhata, though he does not write it in the full generality, but he describes it in when A, B, C are problems in arithmetic progression or problems in interest, whereas Brahmagupta describes the formula for arbitrary ABC. This is the difference. So, I am not saying Brahmagupta invented the formula, but he is the first to state it explicitly and in full generality. Formula was known, of course, to Babylonians, but they did not know how to state a formula, and Aryabhata stated it in specific situations. Sridharacharya describes the method, but and then Bhaskara quotes Sridhara's method for completing the square, a profound idea of far-reaching significance. Now, thanks to the use of negative numbers, India gave a unified treatment of quadratic equations. For a long time, Europe, quadratic equations were discussed separately, ax square plus bx equal to c, ax square equal to bx plus c, ax square plus c equal to bx. These three were discussed separately because a, b, c were always to be positive. Now, the importance of the idea of Madhyaharana, the elimination of the middle. So, this substitution y equal to x plus b by 2, this eliminates the middle term. Similarly, you can eliminate the coefficient of x to the power n minus 1 for a general polynomial, which is called Schönhausen transformation. Now, the importance of that, you can see that when Abhyankar was discussing the resolution of singularities, he says the killing of B1 was the basic trick underlying Zariski's and Hironaka's proofs of resolution of singularities of algebraic varieties of zero characteristic. And also there is a proof, so there is a result of Newton, and Abhyankar gave his own proof of the result, but Abhyankar he calls his own proof as Sridharacharya's proof of Newton's theorem. So, he calls it Sridharacharya's proof because the main idea is the completing the square. Now, so I am just giving things which occur, linear and quadratic equation. So, this is about that expanding basically the computing this nth root in as a power series, which requires Hensel's lemma basically. So, linear and quadratic equations, simultaneous quadratic equations, then there is effective applications in problems on interest and commercial arithmetic, problems in astronomy, simultaneous linear equations in several unknowns, method of elimination, etc. Now, just to give an idea about the importance of algebra, which the formal algebra of Brahmagupta, look at even after Brahmagupta how much struggle the Arabian and early European methods, early Europeans did in solving problems of the type Ax plus b equal to c. So, this will be clear from this. So, 170, let us say, look at this practical problem that 170 apples are distributed equally in 8 closed boxes and 2 are in excess. How many apples are there in each box? So, this is a, now we can identify it as a problem in linear equation 8x plus 2 equal to 170, but when the symbol was not there, when the formation of equations was there, how did people do it? So, there was a thing of rule of false position. So, you say guess a value. So, what can be the value? So, maybe guess is 20. So, if it is 20, then put 20 in 8 boxes and 2 in excess, then what the total number comes up, then you see that it is not 170, it is 162. So, compute the error 8, then divide the error by the number of boxes, and if it is an underestimate, then add that. So, this is the rule. You can see that how complicated the rule is. And similarly, there is a rule of double false position. By the way, do not look down upon this rule. This is really Newton-Raphson method for linear polynomial. So, it contained the seeds of it pushed the Western mind towards Newton-Raphson method. So, it is not the, but the point is that a simple linear equation, it was made so complicated in the absence of algebraic symbolism, concept of formation and processing of equations, use of negative numbers. All these pillars had been developed in ancient India by the time of Brahmagupta. And once the concepts got standardized, the solution of linear equations became easy. Then you see series, summation of series, summation of squares, summation of cubes, geometric progression, and in fact, summation of series is not just this, there are various complicated things which I am given. By the way, whatever I am talking about, all these things are given in my article in Bhavna in April 2023, which is mentioned in the abstract. So, there you will see many complicated things. Then combinatorial results are there. Let me skip this, including the Fibonacci sequence that occurs in Virahanka way back in 600. Roots of binomial surds. So, after this Pratishthan is named after Bhaskaracharya. Bhaskaracharya introduced infinity in mathematics. And how did he introduce? So, he says there is no change in infinity. So, he is explaining, he gave the rule infinity plus minus x is infinity. There is no change in infinity when any number enters or leaves it, that is added or subtracted to it. He gives the analogy, just as the infinite immutable, that means when there is pralaya, then the beings are all absorbed in the Lord, but the Lord does not change. or during Srishti, beings come out of the Lord, but the Lord doesn't change. Similarly, when x is added to infinity, infinity doesn't change. Infinity plus x is infinity and infinity minus x is infinity. So, Bhaskaracharya too takes a bold step of introducing infinity, and this adjunction of idea of adjunction of infinity has now been put on a firm footing in several branches of higher mathematics like analysis or in commutative algebra and number theory, in the valuation theory there. Now, I come to something about this foundation of algebra. So, in Sri Aurobindo's Foundations of Indian Culture, you just look at one sentence he makes. The remarkable feature of the Indian mind was a close attention to things of etc., to systematize and to found in each department of it a science, a shastra. This was characteristic of the Indian mind. And when you read such a sentence, the first image that comes to your mind is Ashtadhyayi, that the grammar, how it has been formalized, which has drawn the admiration for among scholars all over the world, Panini's Ashtadhyayi. But what is not emphasized, and this is a problem because mathematicians are not talking about it, the Kutakadhyaya of Brahmagupta, that also fits here. So, prior to Brahmasphura Siddhanta, there are principles and results which may be identified as belonging to algebra. But one is yet to see a conscious formulation of the science of algebra as a shastra, and that leap is taken by Brahmagupta when he composes a separate chapter on algebra and emphasizes its importance. The chapter begins with a statement regarding the indispensability of algebra, the power of the algebra, and lists its core topics. So, Brahmagupta, how he is promoting algebra. Since questions can scarcely be known without algebra, therefore, I shall expound on algebra with examples. So, by knowing well the pulverizer, so that is the linear Diophantine equation, that Ax minus By equal to C, 0, negative and positive quantities. So, in the definition of algebra, he is introducing 0, negative and positive, unknowns, elimination of the middle term, that means the quadratic equations, symbols, equations with one unknown, equations involving product of distinct unknowns, the what is now called Pell's equation, one becomes among the learned somebody special. So, the point I am trying to say is that here there is a recognition of algebra as a distinct and powerful branch, an indispensable branch of mathematics. That is at the beginning of the chapter, and at the end it is very remarkable what it says, that why algebra, because now every time you have to justify, and anybody in any organization you have to justify why do this, why do that. So, Brahmagupta, so in that time also that there is a justification for algebra. So, you see that various justifications is given. These problems are for one's delight. So, this is a statement of the pure mathematician's attitude to mathematics, for one's delight. Then he says, for them from them thousands of others may be formulated. So, do you say now what is good research? That somebody has done very good research, great research. What is the definition, criterion for great research? One is the impact factor, that how much work it has generated. And that is something which Brahmagupta is saying, that from these principles of algebra, problems raised, thousands of others may be formulated. The problems raised by the others may be resolved by the technique stated. That means it helps you in solving open problems. So, in a meeting of astronomers, one who simply raises the Kutaka related questions dims the glory of others. You know what he is talking about, conjecture. Questions, raising a question, like Ramanujan's conjecture, Well's conjecture, immediately you get this thing. It does not give a proof. So, in a meeting of astronomers, in a meeting of, you just substitute math, in a meeting of one who simply raises questions, dims the glory of others, a well formulated conjecture, Langland's program, like the sun who demolishes the light of the stars. How much more would one achieve if one also knows the solutions, like Delin solution of Well's conjecture and so on. So, you see the three features of algebraic research is implicit here. Internal compulsions, which is what he calls by delight, because he has to use words which people will understand. that is Sukha Matrami Mami, generation of new research and applications. So, Brahmagupta was a pioneering visionary who defined and recognized the importance of algebra, emphasized the need to pursue algebra for its intrinsic mathematical importance. Now, Bhaskaracharya, actually since I have quoted his ending quote, I think this I will skip, but I will just say that at the beginning he gave an, in the invocation, he pays a tribute to the wise mathematician who using algebra solves a problem, and this is analogous to, so he makes a pun. In the same sloka, he also venerates the unmanifested self-existence being of the Sankhya philosophy, who is the cause of the manifested universe. Narayana, another important algebraist, he says, as out of him, as out of the Lord, is derived the entire universe visible and endless, so out of algebra follows the whole of arithmetic with its endless variety of rules. So, there was a recognition that arithmetic is really a part of algebra. Therefore, I always make obeisance to Shiva and also to algebra. Now, I will also give one food for thought, that how the Indian culture was, might have been helpful for the, algebraic ideas. So, this came to me when I was reading The Secret of the Vedas, Sri Aurobindo. So, what I am trying to say is the kind of expressions that Sri Aurobindo uses to describe what is the Veda. So, Veda, as you know, is expressing something which cannot be realized by ordinary intelligence. You have to really raise your consciousness to understand what Vedas is talking about, but Vedas try to help you by using symbols. So, for example, he uses the Veda uses go or cow as a symbol for enlightenment. That is why we say Gaveshana. Gaveshana is goation, that is quest for light, quest for knowledge. So, cow is a symbol for illumination, mental illumination. Horse is the symbol, Ashwa is the symbol for this thing, energy, force, etc. Hound, Sarma, that is for that intuition which straight away goes to the truth. So, he says the Veda is a book of esoteric symbols, almost of spiritual formulae, etc., etc. So, out of the sameness of experience and out of the impersonality of the knowledge received, there arose a fixed body of conceptions constantly repeated and a fixed symbolic language, which perhaps in that early human speech was the inevitable form of these conceptions, because alone capable by its combined concreteness and power of mysticism of expressing that which for the ordinary mind of the race was inexpressible. That means, what is inexpressible you express in terms of symbols. That is what the Veda is about. Now, the term he uses for that is divine algebra, that no pursuit of aesthetic grace, richness or beauty induces these mystic poets to vary the consecrated form which had become for them a sort of divine algebra, transmitting the eternal formulae of the knowledge to the continuous succession of the initiates. So, what I am saying is that Sri Aurobindo is using this mathematical term algebra to express what the Veda is about, that it is something like a divine algebra. So, therefore, this divine algebra comes first. The Veda is of course older to anything else. So, this something that to what is inexpressible to express in terms of symbols, that is inherent in that culture, and therefore, one can surmise that the culture had helped in the basic idea of algebra of expressing what is not known to me, what I am seeking in terms of a symbol, because that is what is there in the Veda, that what cannot be expressed without that reaching that spiritual height. Okay, you tried an approximation in terms of a symbolic thing, and Sri Aurobindo, who knows what the Veda is about, the most appropriate expression he used is the divine algebra. So, this gives me a thought that whether the prevalence of the Vedic culture had helped or set up a conducive environment for the algebra, this thing. And this parallel you can see, that use of symbols in early spiritual treatises to express that which is unmanifested to the seeker, and the use of symbols in later technical treatises to express the unknown quantity which is being sought. And you can see concrete examples. Ishta, the word Ishta you see that it is something which is sought. So, typical use is Ishta Devata, chosen deity whose realization is a seeker's aim. And in mathematics, the Ishta is the term for the unknown. So, you can see the mystic influence in the genesis of algebra. Brahmagupta uses the description, in his description of the Pale's equation, he uses Moolam Dvividha Ishta Vargad. So, Ishta Vargad, that is x square, x1 square, x2 square are called Ishta Vargad. Okay, let me skip this. Now, the last two slides. So, Stilwell has an excellent book, History of Mathematics, Mathematics through History. I think this is something which college students should read. So, he actually raises the question and gives the answer that why algebra is not attributed to Indians and to Arabs. Brahmagupta's work, the high point of Indian mathematics to that time, was more advanced than Al-Khwarizmi's in several respects. Notation, Al-Khwarizmi did not have notation. Admission of negative numbers, Al-Khwarizmi did not have that. Treatment of Diophantine equations is finding integer solutions of equations. Even though it predated Al-Khwarizmi and was very likely known to him. Indian mathematics had spread to the Arab world with the general promotion of culture by the 8th century, and Arabian mathematicians acknowledged the Indian origin of certain ideas, for instance, the decimal system. So, Arabs had always said that this is a Hindu way of doing things. But why then did Al-Khwarizmi's work rather than Brahmagupta's became the definitive algebra? Perhaps this is a case where a mathematical term caught on for accidental reasons, but here, however, it may be that the time was ripe. When the time was ripe in Europe for introducing algebra, the idea of algebra to be cultivated, the simple algebra of Al-Khwarizmi served the purpose better than those of his more sophisticated predecessors. So, the paradox is Brahmagupta's algebra was too sophisticated to get recognition. So, this is the thing that why Al-Khwarizmi is considered father of algebra and not Brahmagupta. So, like in mathematics now, various things are happening in frontiers, but even those who are leading mathematicians, they may not know the details. So, that is the same thing that what Brahmagupta did was so ahead of his time that the recognition. So, like decimal system went from India to Arab, etc. And that is really acknowledged except by those who have a deliberate agenda of not acknowledging. But the algebra, there is a confusion because Brahmagupta's algebra was too sophisticated. So, this has to be understood. And finally, that since I quoted Mumford, you may think that Mumford wrote it in an email in 2013. So, whether it was just the momentary impulse. 10 years later, so what happened is that Mumford's letter is now official because it has been that Mumford's letter to me in 2013 is published in Bhavna with his consent. So, now it is a fixed document. So, naturally out of courtesy the editor had sent the article where he is quoted, the full letter is quoted to Mumford, and then Mumford replied back to the editor of Bhavna, C.S. Arvinda. I still believe wholeheartedly, so this is 10 years after his original statement, that Brahmagupta was the real inventor of algebra. Diophantus introduced one unknown but could not deal with two or with substitution, and this made his writings obscure and convoluted. And the law of composition, incidentally, here I suppose claim some credit that Mumford had not been emphasizing about laws of composition, that modern abstract algebra in Brahmagupta's work, but I think this is an impact maybe of reading my article that now he also emphasizes this, and the law of composition with Pale's equation is true algebra, a clear glimpse of modern abstract algebra. So, whatever I had been saying, he has completely acknowledged it now that Brahmagupta's law of composition is a clear glimpse of modern abstract algebra, that means the college algebra also. And I will just give you one information that on the National Mathematics Day of 2020, Manjul Bhargav had talked about Ramanujan, and at the end he was asked a question that in which other mathematicians you see that magical quality which you see in Ramanujan. And so so this was spontaneous response he gave was 3 modern mathematicians he referred to, that means Andrew Wiles, Barry Mazur and Conway. And then he said, if I go further back, it will be Gauss, and if I go still further, then Brahmagupta. And he says that the kind of ideas that are present in Brahmagupta's Brahmasputa Siddhanta around 600 CE, he used the expression, just blows your mind. So you can get a glimpse at why it is so. So finally, at least there is an institute named after Bhaskaracharya where we have assembled. But there is hardly anything named after Brahmagupta in India that I am aware of. One exception is the hostel in TIFR. And C.S. Arvinda and I both were in TIFR. So when my article, when I sent this article, and fortunately he was also visiting TIFR, he took a photograph and published it in Bhavna. This is the only place I know where Brahmagupta's name is mentioned, which is a pity. And the kind of attitude we have, it is good that now there is talk of ancient Indian mathematics. I came to know of ancient Indian mathematics around the turn of this century, this 2000, around that time. And maybe 2002 or 3, sometime the director of our institute introduced a special fellowship, what is called PhD fellowship, which would be higher than the usual fellowship. So it is like CSIR, it has the usual fellowship, but some exceptional students are granted higher fellowship, which is called Shyama Prasad Mukherjee fellowship. So an analog of that he introduced in ISI, and only one student in mathematics will get, one student in statistics, like that. Incidentally, my student Nina Gupta was the first and perhaps till date only person selected in mathematics for that special fellowship. Now, when that was introduced, Professor K.B. Sinha, the then director, he had asked for a suitable name for that fellowship. And he said that it should not be named after Mahalanobis or Jawaharlal Nehru, because it becomes hackneyed. I mean, there are so many things named after them, and it should introduce something about the institute's originality. So he asked a professor to look for a name. So that professor came to me, and I said that the right name is Brahmagupta. The fellowship should be named after Brahmagupta. So people were taken by, suddenly something this comes up. So it was taken, so final decisions are made by ISI Council. And ISI Council government representatives are there. And that time the BJP was in power, by the way. And the decision was, let us not name it after anybody. This was the situation at these are historical facts, so we are in history. So this was the recognition of Brahmagupta at the beginning of the 21st century. And I am really curious, who was it in TIFR who thought of naming a hostel after Brahmagupta? And if somebody can come across that, that would be something exceptional, like naming Bhaskaracharya Pratishthan. Say now we have got used to the name, but naming it in the 50 years ago, I am founding an institute, naming it after Bhaskaracharya, that requires a real originality, I would say, which was very characteristic of the man. Anyway, thank you. If you have any question. Thank you.